Hello, and welcome to Empowered Learning. Um, Thank you for checking out this particular video. This video will be about solving systems of linear equations using the substitution and elimination methods. Um, just to let you know, the elimination method is also known as the addition method. So depending upon what textbook you may be using or how your instructor may be teaching it, you may hear the elimination method as the addition method. Okay, so the things that we want to talk about are what it means when we actually solve a system of linear equations. So what that means conceptually, um, what do our solutions look like whenever we use our strategies to solve a system of linear equations. How are we going to know um, from the types of solutions that we know to expect to get, what tips us off to let us know that, hey, this solution is one single point, or this solution is infinitely many, or what have you. Okay, so we're going to talk about that as well. We're also going to get into some of the basic definitions or some of the nomenclature around systems of linear equations so that we can be familiar with that as well. Okay. So to start off, let's look at some definitions here. So we see that when we talk about a system of equations, it's basically a collection of two or more equations where each equation contains one or more variables. Okay, and so when we get into talking about systems of linear equations, the difference is that all the equations that we're considering in the system are equations of lines, basically. And so we see that is being demonstrated in terms of the slope-intercept form, which you see here, as well as the standard form. And so more so the standard form of an equation of a line is the form that's most used whenever we deal with systems of linear equations. Okay? So moving forward here, whenever we are solving systems of linear equations, what we're really trying to do is figure out, if we have two lines, where do they cross? Okay, that's essentially all we're trying to do. We can solve systems of linear equations graphically, or we can do it algebraically. When we do it graphically, the way that we do is just draw each line that's in the system, figure out where they cross. Okay, and so this is an example of what I have here. Whenever we have systems of linear equations, we know we have three different outcomes. The first outcome is that the two lines actually intersect at a single point. And so that's what figure A is about right here. The way that we express this point here is we're going to have some x coordinate and some y coordinate. So we'll know whenever we're dealing with systems of linear equations, when we do it the algebraic way, that we have one solution, because we would get a particular value, real number value for x and a real number value for y. In the case of our lines not crossing at all, that would be the case of we have no solution. Okay, and so we know that lines do not cross only when their slopes are parallel. Excuse me. We know that lines do not cross whenever the slopes are the same and their y-intercepts are different. And that means that the equations are parallel to one another. So that's what I was trying to say. The last case is a case where we have a system of equations to where, in this case, we have two lines, and both lines, even though they look different, they are the same. Okay, and so a quick example of that would be something like this. So let's say we had the system of equations where we have x minus y is equal to 2. And then let's say we had 2x minus 2y equals 4. In this instance, we see that the only difference in between equation 1 and equation 2 is that the second equation is just the first one where both sides are multiplied by 2. In that instance, these are the same line because, of course, if we divided both sides by 2 here, we would just get x minus y equals 2, which is the same as our first equation. So in this instance, we say that we have infinitely many solutions because what the lines are doing is essentially crossing through or shooting through one another. So every point on that line will be intersected with the other line, which is essentially the same thing. So this point, 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 so on and so forth will be the same. So in this situation, we say that we have infinitely many solutions. Okay. Whereas here for the parallel ones, we say that we have no solution. And so we want to make sure that we understand that before we even do anything else as far as trying to graph these, or if we were trying to use the strategies of substitution or elimination to be able to solve these equations. Solve these systems, rather. All right, so moving on to talk about some definitions here. We know that when lines intersect at exactly one point, we have one solution, and that went with figure A. And so we know that the system is considered to be consistent, and consistent just means that the system has at least one solution. Okay. So we also know that the linear equations are independent of each other, and what that means is that there are no equations in the system that are identical. We also know that the slopes of the lines are not equal in these cases. So we know our line, one is going to look like this, another one may look like that. Okay, and so that's an example where the slope of one line is positive, the slope of the other line is negative. If we have an instance where both lines are positive, have a positive slope rather, then it would look something like this. Okay. All right, so next we want to talk about when the lines in the system do not intersect at all. Okay, so this went along with figure B on the previous page. And so from here, we understand that the lines are parallel, and what that means in terms of equations of a line is that the slopes are the same, but the y-intercepts are different. And of course, if we draw lines that are parallel, that would make sense. If the lines are parallel, then that means that the slopes are the same, and thus these lines will never be able to cross one another. But let's just say we take these two lines here, you see that their y-intercepts are different. And so that brings the separation in between the two to let us know that they are indeed parallel. Since these lines do not cross, they're said to have no solution, and thus the system is considered to be inconsistent. Okay? If you remember, consistent means that the system has at least one solution. So inconsistent, from what we see up here, would be a situation where the system has no solution. Okay? Now, for figure C, this case will basically be the case where we have lines that are identical. Okay, and so we know that when the lines are identical, they have to have the same slope as well as the same y-intercepts. Okay, and we also know that in this case the system is consistent, meaning that it has at least one solution, and coincident system is also that. And if you see from up here, coincident basically means that there's at least two equations in the system that are identical to one another. Okay. So with that, the last thing that we want to say is that linear equations are what we call dependent if they are in a situation where you have infinitely many solutions. Okay?